Hello and welcome. Today, we're diving deep into Earth's history to understand its climate, long before we had thermometers or satellites. This field is called paleoclimatology, the study of past climates. Why look back millions of years? Because understanding how Earth's climate naturally behaved in the past gives us crucial context for the changes we're seeing today and helps us anticipate the future. Paleoclimatologists are like environmental detectives, using natural archives, often called proxies, to uncover clues about ancient temperatures, rainfall, and even the air composition. One powerful technique involves drilling into ancient ice sheets in places like Antarctica and Greenland. These ice cores contain trapped air bubbles, tiny samples of past atmospheres. Analyzing them tells us exactly how much carbon dioxide and methane were in the air hundreds of thousands of years ago. The ice itself also records temperature information. Then there are tree rings. Most trees grow a new ring each year, and the ring's width reveals the conditions. Was it a good year, warm and wet, or cold and dry? By studying rings from very old living trees and even fossilized wood, scientists build climate timelines stretching back thousands of years for certain regions. We also look at sediment cores drilled from ocean floors and lake beds. Ocean sediments contain tiny fossil shells whose chemistry reflects the ocean temperature when they formed. Lake sediments preserve pollen grains, showing what plants lived nearby, which in turn indicates the climate. Corals, similar to trees, have annual growth bands. Their skeleton's chemical makeup reveals past sea surface temperatures, especially useful for understanding tropical patterns like El Niño. Even cave formations, like stalactites and stalagmites, hold clues. Their layers contain isotopic signatures that tell us about past rainfall and temperature shifts. So what have these techniques revealed? Paleoclimatology confirmed the Great Ice Ages, cyclical periods driven by subtle changes in Earth's orbit. Crucially, ice cores showed us that over the last 800,000 years, atmospheric CO2 naturally cycled between about 180 parts per million during cold periods and 280 during warm periods. Today, we're at about 420 parts per million, far outside that natural range and completely unprecedented in that vast time frame. The records also show climate can change surprisingly fast. There have been abrupt shifts in the past, sometimes happening over just decades. Studying ancient warm periods, when CO2 was naturally higher, gives us glimpses into potential future climates, though they aren't perfect comparisons. Why does all this ancient history matter now? Firstly, it provides context. It clearly shows that the warming we've experienced recently is extraordinary compared to natural fluctuations over millennia. Secondly, these past climate reconstructions help us test and improve the computer models we use to predict future climate change. If a model can accurately simulate past climates, we have more confidence in its future projections. Finally, paleoclimatology helps us understand Earth's climate sensitivity, how much the global temperature changes in response to rising greenhouse gases. In conclusion, by piecing together clues from ice, trees, sediments, and more, paleoclimatology gives us the long view on our planet's climate. It highlights the powerful role of greenhouse gases and underscores that the changes happening today are rapid and significant, even when compared to vast stretches of Earth's history. Understanding the past truly is key to navigating our climate future. Thanks for listening.